Hello everyone, uh, welcome to the fourth tutorial of this course. So today I will be solving the assignment 4 from last year's course, and if you have any problem regarding the lectures or any previous assignments, you can unmute and ask, or you can write in the comment section. Okay, so let me share the screen. So I have shared the screen. If you cannot see, any of you cannot see it, you can tell me or you can write. Okay, so this is the first problem. The problem, it says the local maxima of the function f of xy, which is x cube plus y cube plus 3x square minus 3y square minus 8. So you are asked to find out the local maxima of this given function. So first of all, let's find out the critical points. So to find out the critical points, we need to take the partial derivative. So del f del x equals to, so del x of x cube plus y cube plus 3x square minus 3y square minus 8. Now if you take the partial derivative with respect to x, it will be 3x square plus this term will be 0, this term will be 6x, and the others will be 0. So let's write it 3x square plus 6x. Now for a critical point, the value of del f del x, it will be 0, and it basically says x can take two values. So you can write it like x times 3x times x plus 2 equals to 0, and it says x can take two values, which is 0 and minus 2. And also if you take partial derivative with respect to y, it will be del y of this x cube plus y cube plus 3x square minus 3y square minus 8. It will be 3y square. The first term will be 0, the second term will be 3y square, third term will be 0, derivative of third term, and derivative of fourth term it will be minus 6y, and derivative of last term will be 0. So now if there is a critical point, its value will be 0, and from there you take 3y common, will be 3y times y minus 2 equals to 0, and you will have two values of y, which is 0 and 2. So basically the critical points are, so x can take two values 0 and minus 2, and y can take two values 0 and 2. So the critical points are say x0 0, x0 y0. So it's a set of 4 points. So for x equal to 0 there can be two y values, that is 0 and 2, and for x equal to minus 2 there can be two y values, which is again 0 and 2. So the points are 0 0, 0 2, minus 2 0, and minus 2 2. So there are 4 critical points. Now let's check uh, which of this is maxima, which of this is minima, and which of this is saddle point. So to do that, we need to take the second order derivative, second order partial derivative. So basically we need to find out the discriminant, that is, so it is already defined in the class. So D is AC minus B square, where A is del 2F del x2, B is del 2F del x del y, and C is del 2F del y2. So there is a half, but since we will be talking about whether this D is greater than 0 or less than 0, the half will not matter. If something is less than 0, then half of it will also be less than 0. So let's calculate then del 2F del x2. So A is del 2F del x2, which is del x of del f del x, and we have already calculated del f del x, which is 3x square plus 6x. So it is del x of 3x square plus 6x. That is 6x plus 6. Now if you calculate B, it will be del x of del f del y. So del x of del f del y you already calculated, that is 3y square minus 6y. So 3y square minus 6y, and del x of it will be 0. There is no explicit x dependence, and value of C will be del y of del f del y, which is del y of, so del f del y is 3y square minus 6y, which is 6y minus 6. So these are the values of A, B and C. So now let's consider this 0 0 point. So let's see whether this, so if x0 y0, whether this 0 0 point is a maximum or minimum. So if x0 y0 is 0 0, in that case A at that point is 6, B is always 0, and C at 0 0 it is minus 6. So in that case the value of D discriminant is AC minus B square, which is minus 36. So basically we have D that is less than 0. It implies that 0 0 is a saddle point. So now the next point we have is 0 2. So let's check whether that critical point 0 2 it is a maximum, minimum or saddle point. So for x0 y0 equal to 0 2. So for this point A, so it is 0 2, that means A is 6, A is 6x plus 6, and if you put x equal to 0, then it will be 6. So a is 6, b is always 0, it doesn't depend on x and y, and c is 6y minus 6. So c is 6y minus 6, and now if you put y equals to 2, in that case it will be 12, and 12 minus 6, it will be 6 plus 6. So in that case, the discriminant d, it will be ac minus b square, which is 36. So d greater than 0, it means there exists a, so this point is either a maximum or minimum. So in that case we need to look at a, and now as x is greater than 0, in that case, so sorry, you need to look at a. So d greater than 0, it means there exists a maximum or minimum, and as a also greater than 0, it means 0 to is a local minimum. So 0 to point is a local minimum. So we need to find out, so in this problem 1 you need to find out the local maximum. So we are still not there. So let's check for this point minus 2, 0. So this is our third critical point. So x0 y0 equals to minus 2, 0. So for this point a is 6x plus 6. So a is 6x plus 6, and if you put minus 2 at the place of x, it will be minus 12, and minus 12 plus 6, that is minus 6. So a is minus 6, b is always 0, and c is 6y minus 6, and y is 0. So in that case it will be minus 6. So it will be minus 6. So our discriminant will be ac minus b square, which is 36, again positive. So that means this 2 minus 2, 0, it is a point, it is a critical point, and it can be maxima, either maxima or minima. So now if you look at the a value of a, it is negative, and it says this point is a local maxima. So d greater than 0 and a less than 0 implies minus 2, 0 is a local maxima. So there is only, so we already got our answer. So our answer will be minus 2, 0. It is local maxima. So local maxima is minus 2, 0, and there is only one critical point left to check. So let's check it anyway. So point left is minus 2, 2. So for x0 y0 equals to minus 2, 2. For this critical point a is, so a is 6x plus 6. So 6x plus 6. Now if you put x equals to minus 2, in that case it will be minus 12 plus 6, and it will be then minus 6. If you calculate, it will be minus 6. Minus 6. B is always 0, and C is 6y minus 6. So if you put, so it is 6y minus 6, and if you put y equals to 2, then it will be 12 minus 6, which is plus 6. Then D is AC minus B square, which is minus 36. So D less than 0, it implies minus 2, 2 is a saddle point. So we have tested all the critical points, all 4 critical points. And our answer is, so the local maxima for this function, it will be at point minus 2, 0. So now let's look at the next problem. So hope you can see the problem, second problem. So you are given the same function again, which is x cube plus y cube plus 3x square minus 3y square minus 8, and you have to find out the local minima. The local minima. So we have already calculated here. We have calculated the critical points and we have already tested for maxima and minima. So the local minima we got, that is at point 02. So there at point 02 we got the local minima. So you can immediately answer it. That is, the answer will be 02. So for this solution, look into solution of problem 1. Now the next problem, so in problem 3 you are given a function that is f of xy equals to x to the power 4 minus y to the power 4, and you have to find out the number of saddle points. So let's find out then the critical points. So del f del x equals to 0, it gives x3 x cube equals to 0, and it gives x equals to 0. There are okay, so it gives x equals to 0, and del f del y equals to 0 implies minus 3y cube equals to 0, which says y equals to 0. So there is only one critical point, that is, so at x0 y0 the critical point, there is only one critical point, that is 0 0. Only one critical point. So now let's check whether this critical point, it's a saddle point or maximum or minimum. So for that we need to do the second order partial derivative test. So let's calculate del 2f del x2. So del 2f del x2 is, so del x of del f del x, and del f del x is 3x cube, so it will be 9x square, and del x of, so it is del 2f del x del y, it will be del x of del f del y, and del f del y you already calculated, that is minus 3y cube, so minus 3, sorry, so let's write it. So del f del y is minus 3y cube, and if you take del x of it, it will be 0, and del 2f del y2, it is, so del f del y is minus 3y cube, so it will be minus 9y square. So now del f del x, del 2f del x2 at 0 0, it is 0, which means basically a equals to 0, and b is 0 because del 2f del y2 is always 0, and c equals to del 2f del y2 at point 0 0, because that is our critical point, and its value is also 0. So in that case, the value of d is 0. That means the second order partial derivative test, it is inconclusive. Partial derivative test is inconclusive. So you cannot conclude anything from this second order partial derivative test directly. So, but you still have so asked to find out, you are still asked to find out the saddle number of saddle points. So there is one way to check whether it is a saddle point or not. So if you plot this function, so in 3D, if you plot this function as, so let's say z equal to x to the power 4 minus y to the power 4. So in that case, so let's plot it. Okay. So if you plot x to the power 4 minus y to the power 4, it will look like this. So you can see the plot, right? So this is how it will look like. So the saddle point, so if you visualize the saddle point, it is it looks like, so if you look from this, so this is the z axis, this is the y axis, and this is the x axis, and this is the y axis. So now if you look along the x axis, so then you will see that it's a minima, you know, if you look along the x axis, and if you look along the y axis, it's a maxima. So this is why it is called a saddle point, neither a maxima nor a minima. So it's like a back of a horse, you know. So from one direction you will see it's a minima, but from other direction you will see it's a maxima. So basically 0 0, so looking at the plot, looking at the graph, you can say that 0 0 is a saddle point. So there is also another way, if you can calculate whether it is a saddle point or not. That is, so the f of xy, it is given as x to the power 4 minus y to the power 4. It can be written as x square minus y square times x square plus y square. So let's write x square minus y square as hx, h of xy, and x square plus y square as let's say g of xy. So in that case, fx is h of xy times g of xy. So now fx is the multiplication of these two functions, h of xy and g of xy. Now if you plot this g of xy, it's basically a kind of cone in it's a paraboloid in 3D. So if let's say g of xy, that is x and y, so it will look like a paraboloid. And now if you look for this, if you look for the saddle points or the maximum critical points in this h of xy, that is x square minus y square, you will see, so its plot will look like the same I showed in the 3D plot of saddle point. So it's x and y is h of xy. So if you test it for the saddle point, you will also get that 0 0 is a saddle point for this h of xy. So it will look like, so if you look from this x direction, so you will see like it looks like this, and if you look from the y direction, it will look like this. So basically this point is neither a maximum nor a minimum. And now if you multiply it with this g of xy, so then the points where it is getting negative, so g of xy it is always positive, so it will behave like behave in a similar manner. So like where it is getting negative, and if it is multiplied with a positive number, so then it will also the f of xy, it will also be negative, so it will look like it will look like, if you look along x, it will be a maxima, and if you look along the y axis, it will be a minima. So it preserves the kind of its property if you multiply hx with g of xy. So from there you can conclude that this 0 0 point, the critical point, it's a saddle point. So but not from directly from the second order partial derivative test. So basically the number of saddle points, the answer will be 1. So now the next problem. So in the problem 4, you are asked, so if f and x in suffix, so it means del x of f at point AB, and it means del f del y at point AB. So it is given that, so both this partial derivative at point AB, so these are 0. So then the statement is, if these partial derivatives, first order partial derivatives are 0 at point AB, so then f must have a local maxima or a local minima at point AB. So it is not the case. Actually it can also be a saddle point. So the statement is then false. So now the next problem. So in this problem 5, This problem statement is Lagrange multiplier method can be applied for unconstrained optimization problem also. So we have already seen how the Lagrange multiplier method is applied in the constant optimization problem. So what it basically does is, so let's say there is a function, let's say two variable function f of x y something, so it can be anything. So let's say you are asked to maximize a you are asked to optimize this f, and the constant is, let's say, g of x y equals to 0. So in that case you can apply Lagrange multiplier method, and it's like, so lambda is Lagrange multiplier. You basically put the two functions together. So what basically this lambda does, so you basically formulate a function that is f of xy plus or minus lambda of g xy. So you are basically forming a function L, which is a function of x, y, and lambda. So you are basically making lambda a parameter, and then the equations are like gradient with respect to L, that is 0, and with respect to lambda is 0. So for with this you will basically get this same equation, this constant equation. So now you don't have any constant, so you have unconstant optimization. So in that case, if you apply Lagrange multiplier method, it will not affect the problem, but you can still apply. So for example, let's say you have f of xy, so you are asked to optimize this f of xy, and your constant equation, let's say, I mean you have no constant in the plane of xy, so you have some other constant. So let's say there is a z, and you have z equals to something given. So this constant doesn't affect the given optimization problem. This given optimization problem is it is basically unconstant. So you can anyway apply Lagrange multiplier method, and you can put these variables together. But during the optimization, so if you do this operation, that is gradient with respect to x and y of L, if you formulate L and you do this, so the constant part, it will go away. So it will not affect the equations. So you can still apply. So the conclusion is you can still apply the Lagrange multiplier method. You can still apply, take Lagrange multiplier and do the calculations, but it will not affect the problem. So it is apply. It can be applied for unconstant optimization problem. The statement is true. So now the next problem is, you are asked to find out the distance from the origin of a point on the curve of x y square equals to 54, which is nearest to the origin. So basically you are asked to find out a point on this curve. So you are asked to find out a point on this curve x y square equals to 54, such that the distance between the point and the origin, that will be minimum. So basically you need to minimize. So let's say, so you are in 2D, so that means, so you are asked to find out a point xy such that the distance between this point xy, if we write it by d, then its distance is given by x square minus y plus y square, that is the distance between this point xy and 0, the 0 0, that is the origin. So that will be minimum. So you basically asked to minimize this distance, and you have a constant, that is, so you need to stay on this curve, that is the constant you have. So the constant is basically g of xy, which is xy square minus 54 equals to 0. So this is the constant, and you are asked to minimize this distance. So we will apply the Lagrange multiplier method. So if you look at this expression, this distance, so there is a root here. So now if you define f of xy as d square equals to x square plus y square and g of xy like this, and if you minimize this, if you minimize this f of xy, that is d square, distance square, it will automatically minimize the distance also. So why I am doing for the square of distance? It's because there is no root. So derivating here, taking the derivative, if we have a root, it will be difficult. So for simplicity, I am minimizing this d square. So it will anyway, it will give the point. So which also minimize the distance d. So then basically what you have is gradient of f of xy is equals to lambda. So lambda is the Lagrange multiplier, and g of xy, you have this, and along with this you have this equation, this constant equation. So the gradient of this f of xy, it will be, so del f del x, so vector, so del f del x comma del f del y equals to lambda times del g del x comma del g del y. Now del f del x is 2x comma del f del y is 2y, so 2y equals to lambda times del g del x. So del g del x is y square, so this is the g of xy, del g del x is y square, and times lambda, there will be lambda y square comma del g del y is twice of xy, so, and there is a lambda here, so it will be 2 lambda xy. So we basically have three equations, which is 2x equals to lambda y square, another one is 2y equals to 2 lambda xy, and the third one is the constant equation, that is xy square minus 54 equals to 0. Xy square minus 54 equals to 0. So now from here, you can say y equals to lambda of xy, and okay, so y will also get cancelled, so if y not is equals to 0, so y cannot be 0, it's because it will not satisfy this constant equation. Okay, so we can cancel y from each side, so that basically gives x equals to 1 by lambda, so y not is equals to 0. So x equals to 1 by lambda, and now, so if you put lambda here, so in this equation if you use this, so it will be 2x equals to 1 by x y square. In place of lambda I am writing 1 by x, so it is basically 2x square equals to y square. So we have y square equals to 2x square. Now in this constant equation, let's put y square equals to 2x square. So in that case, this equation will be 2x cube equals to 54, and we will have x cube equals to 27, and x equals to 3. So with that, so we got x equals to 3. Now if you put this value of x here, you will get lambda equals to 1 by 3, and y, so y square is basically 2x square, which is 2 times 9 is 27, sorry 18, and y is equal to plus minus root under 18. So basically the points are x0 y0 equals to 3 plus root under 18 and 3 minus root under 18. So for these 2 points the distance will be minimum, and the value of the distance, it will be, so d is root under x0 square plus y0 square, which is 3 square plus minus 18 square, plus minus root under 18 square, which is root under 9 plus 18, which is root under 27. So the distance, the minimum distance is root under 27. Now the next problem, so the next problem is again you are given an equation of a plane, and you are asked to find out a point on this plane that is closest to the point 1 1 1. So let's say the desired point is x y z. So in that case the distance between this x y z and the point 1 1 1, it is d equals to root under x minus 1 square plus y minus 1 square plus z minus 1 square. That's the distance. So that's what you have to minimize. So we are asked to find out the closest distance. That means we need to minimize this distance, and the point, it must be on this plane. So this is the constraint we have. So we cannot go outside this plane. So the constraint equation is, so g of xy, it equals to x plus 2y plus 3z, x plus 2y plus 3z minus 13 equals to 0. So basically we need to minimize this d. So anyway we can define a function f of xy that we will minimize and define it like d square, because we don't want to deal with this root. So in that case z minus 1 whole square. So now the problem is you need to minimize this f of xy, which is d square, and we have the constant that is g of xy. So let's use Lagrange multiplier method. So gradient of xy equals to lambda of gradient of g of xy, and if you take this gradient, it will be, sorry, it is xyz. So f is a function of xyz, g is also a function of xyz. So it is xyz. So it will be del f del x, so vector, so del f del x, del f del y, and del f del z equals to lambda times del g del x, del g del y, del g del z. Okay, and so del f del x is, so x is this, so del f del x is twice x minus 1, twice x minus 1. Similarly, del f del y is twice y minus 1, and del f del z is 2 times z minus 1, equals to lambda times del g del x. So del g del x is 1, so it is lambda, comma del g del y is 2, so it is 2 lambda, comma del g del z, so you have 3z in g, so it will be 3, and times lambda, so it will be 3 lambda. So we basically have then 4 equations. So the equations are 2x minus 1 equals to lambda, and another one is 2y minus 1 equals to 2 lambda, the other one is 2z minus 1 equals to 3 lambda, and the last one is the constant equation. So now if you calculate the value of lambda from these three, so if you express x, y, z as a function of lambda, so then it will be x equals to lambda by 2 plus 1, y equals to lambda plus 1, and z equals to 3 by 2 lambda plus 1. So we have x, y, z in terms of lambda, and now if we use this constant equation, it is x plus 2y plus 3z equals to 13. So x plus 2y plus 3z equals to 13, and now if you put this value of x, y and z in terms of lambda, you will get lambda by 2 plus 1 plus twice y, that is 2 lambda plus 2 plus 3z is 9 by 2 lambda plus 3 equals to 13. So now if you do this calculation, it will be 2 lambda plus 4 lambda plus 9 lambda equals to 13 minus 6, which is 7, and here you will have 14, so 9 plus 1 plus 4, 14 lambda by 2 equals to 7. It implies, so 2 and 14 is 7, and it implies lambda equals to 1. So then you will get basically the point, the desired point, that is x equals to lambda by 2 plus 1, so that is 1 by 2 plus 1, that is 3 by 2, y equals to lambda plus 1, that is 1 plus 1 equals to 2, and z equals to, so let's call it x0, y0 and z0, z0 equals to 3 by 2 lambda plus 1, and lambda is 1, so it is 3 by 2 plus 1 equals to 5 by 2. So the point is x0, y0, z0, point is 3 by 2, comma 2, comma 5 by 2. So this is the point which is on this plane, and the distance between this point and this point is minimum with respect to all the points that exist in this plane. So the answer is 3 by 2, 2, 5 by 2. Now the next problem. So in this problem we are asked to find out the length of this curve, which is given by this radius vector, which is t I hat plus cos hyperbolic t j hat. So cos hyperbolic t is basically e to the power t plus e to the power minus t by 2. Sine hyperbolic t is e to the power t minus e to the power minus t by 2. So the arc length is given by, so L, so L is from 0 to 1, so from t is equal to 0 to 1 r dot, that is the velocity, so magnitude of r dot times dt. So it is basically ds or dl, so infinitesimal distance, and you will add up this distance and you will get the entire length of this curve. So let's find out this r dot. So r dot is, so it is dr dt, that is, so I hat plus, so I hat plus ddt of cos hyperbolic t. Now if you take this derivative of cos hyperbolic t, that is e to the power t plus e to the power minus t by 2, and there is j hat. So if you take this derivative, it will be I hat plus derivative of e to the power t is e to the power t, and minus e to the power minus t, derivative of it is minus of e to the power minus t. So it is basically sine of hyperbolic t. So it is I hat plus sine hyperbolic t j hat. So that's the velocity vector. So in that case, the magnitude of it will be root under 1 square plus sine hyperbolic square t, which is root under 1 plus sine hyperbolic square. So it is 1 by 2 e to the power t minus e to the power minus t square, which is 1 plus 1 by 4 e to the power 2t plus e to the power minus 2t minus 2. So 2 times e to the power t minus e to the power minus 3, that is 1. So you will have 2. Now if you do this calculation, you will get 1 by 4 e to the power 2t plus e to the power minus 2t plus 2, which is 1 by 2 times e to the power t plus e to the power minus t whole square. And so this function inside this third bracket, it is basically cos of hyperbolic t, and you are squaring it and then you are taking again root, so it will be cos hyperbolic t. So in that case, the arc length L, it is integration from t equals to 0 to 1 cos hyperbolic t, which is the modulus of velocity vector times dt. So now t equals to 0 to 1, so cos hyperbolic t, you can write it as 1 by 2 to the power t minus e to the power minus t dt. And now if you do the integration, it will be 1 by 2 again e to the power t plus e to the power minus t, sorry, there is no dt, sorry, cos hyperbolic is plus e to the power t plus e to the power minus t. So if you do the integration, it will be minus here, and the limit is 0 to 1. So if you put the limit, it will be 1 by 2 e to the power 1 minus e to the power minus 1 minus 1 by 2 e to the power 0 is 1 minus e to the power minus 0, which is again 1. So this is 0 and this is basically sine hyperbolic of 1. So we have the distance, the arc length of this given curve, that is sine hyperbolic of 1. So the correct answer is the last one. So you can anyway use the formulas involving these hyperbolic functions, but I don't know whether you know those things, so I derived all of them. So this was problem 8. So problem 9 is you are asked to find out the unit tangent vector. You are asked to find out the unit tangent vector of this curve. So the tangent vector is given by, so basically you are asked to find out the unit vector along the tangential direction. So the curve is given, so any tangent vector it will be given by dr t dt, which is direction of any tangent vector, that is given by, so if you take the derivative it will be minus 3 cos square t sin t d I hat, sorry j hat, plus 3 sin square t cos t k hat. So this is a vector along this tangential direction of this curve. So now you have to find out the unit vector, unit tangent vector. So in that case, so it's a, let's say it's a vector along the tangential direction, let's call it tau. So then the magnitude of tau, it will be root under 3 cos square t sin t whole square plus 3 sin square t cos t whole square, which is root under 9 cos to the power 4t sin square t plus 9 sin to the power 4t cos square t. And if you take this 9 cos square t sin square t outside this root, so it will be 3 sin t cos t times root under sin square t plus cos square t, sorry, sin square t plus cos square t, which is 1. So basically the mode of this vector is 3 sin t cos t. So unit vector along this tangential direction, let's call it tau hat, which is tau vector by modulus of tau, that is, so tau vector is 3 cos square t minus 3 cos square t sin t j hat plus 3 sin square t cos t k hat by 3 sin t cos t, which is minus cos t j hat plus sin t k hat. This is the unit vector along the tangential direction. So minus cos t j hat plus sin t k hat, the second option. And the last problem, it is similar to problem 8. So you are basically asked to find out the length of this curve, so the arc length. which is the same curve of problem 9. So here we already calculated the, let's say, the drdt vector. Okay, so we calculated the magnitude of this drdt vector. So this magnitude of r dot, that is already calculated, and that is the magnitude of tau, basically, that is 3 sin t cos t. 3 sin t cos t, which is basically 3 by 2 into sin t cos t, that is 3 by 2 sine of 2t. And you are asked to find out the length of this curve from t equals to 0 to pi by 2. So basically the length L is equal to t equals to 0 to pi by 2 r dot magnitude times dt, and it is t equals to 0 to pi by 2. This magnitude of this r dot is 3 by 2 sine of 2t dt. Now if you do this derivative, it will be 3 by 2 minus cos of 2t by 2 from t equals to 0 to pi by 2. 3 by 4, let's say, minus cos of 2t from 0 to pi by 2, which is 3 by 4 minus so cos of 2t, and the upper limit is pi by 2, it will be minus cos of pi minus cos of 0. Cos of pi is minus cos of pi plus cos of 0. So cos of pi is minus 1 and cos of 0 is 1. So in that case you will have 3 by 2, 1 plus 1, that is 3 by 2. 3 by 4 times 2, that is 3 by 2. So the length of this curve is 2. Okay, so these are the 10 problems from the 4th assignment. Gagan is asking the discriminant is defined as AC minus B square. Is the discriminant formula not? Can you please explain? So this discriminant, it is for one variable. So I mean, I don't think it can be compared, like, so A is like, so here the A is defined like if you have a function of, let's say, 2 variable, f of xy, so then A is defined like del 2f del x2, B is defined like del f del 2f del x del y, and C is defined as del 2f del y2. So in case of, let's say, you have a function like f of g of x, which is let's say, so this is, let's say, x square some plus something, so x square plus bx plus c, something like that. So in this case, the point, the discriminant that you are talking about, that is b square plus 4ac, it is kind of different. So you are not asked to maximize this function or something like that. So here you are asked to find out the roots. So this so you cannot compare this kind of definition of discriminant. So here you are talking about this quadratic equations and all. So you cannot compare this with this definition of discriminant. So here you are asking to maximize a many variable multivariable function. you are not asked to find out the root. So these are different actually. So if you see, there is no maximum or minima idea here. So in this the way you are saying the discriminant like b square minus 4ac. So it is just to find out the root of a quadratic equation. Okay, so that's all. So if you have any questions regarding the problems or regarding the problem of your this year's assignment, you can ask. Otherwise, you can leave one by one.